will be the lecture over section 27.4. If L naught is the distance between 2 points that are at rest in the particular frame of reference, it is called the proper length. If this first frame is moving with a constant velocity u relative to a second frame, and the distances in the frame are measured parallel to that frame's velocity, then the distance L between the points, as observed in the second frame, is going to be shorter. And that's done according to this particular formula. And this effect is called length contraction. So a ruler oriented parallel to the frame's velocity and moving with respect to an observer appears shorter than when measured in a frame at rest in the observer's frame. So you can see here, you've got the source and the mirror, and so you got some sort of distance here. You've got Justin out here, you've got Julianne in here in the moving reference frame. So in Julianne's frame of reference, the light pulse travels a distance L naught. In Justin's reference frame, the light pulse travels a distance of L plus U times T1. So the length contraction here is that this distance is going to be smaller than this distance. So just as the time interval between two events depends on the observer's frame of reference, the distance between 2 points also depends on the observer's frame of reference. So the concept of simultaneity is involved. So suppose you want to measure the length of a moving car. One way is to have two friends make marks on the pavement at the same time at the positions of the front and rear bumpers. Then you can measure the distance between the marks. If you mark the position of the front bumper at one time and that of the rear bumper half a second later, you won't get the car's true length. But we've learned that simultaneity isn't an absolute concept, so we have to be very careful to treat times and time intervals correctly in different reference frames. So to develop a relationship between length and various coordinate systems, we consider another thought experiment. We attach the source of light pulses to one end of the ruler and a mirror to the other end. And the ruler is at rest in reference frame S prime, and its length is that frame, its length in that frame is L naught. Then the time delta T naught required for light pulse to make the round trip from source to mirror and back is given by this. This is a proper time interval in S prime because departure and return occur at the same point in S prime. In reference frame S, the ruler is moving to the right with speed U during the time the light pulse is traveling. The length of the ruler in S is L, and the time of travel from source to mirror, as measured in S, is delta T1. During this interval, the ruler, and with source and mirror attached, move the distance of this. So the total length of path B from source to mirror is not L, but this. The light pulse travels with speed C, so it's also true that this is the case. And combining these two equations, we can find this. In the same way, we can show that the time delta T2 for the return trip to mirror the source, as measured in S, is this. Total time for the round trip is the sum of those. It comes to this. And we also know that these two are related by this equation. So when we solve equation 27.6 for this and substitute in the result that we have from equation 22.7, which is right here, we come up with this. So finally combine this equation with 27.8, eliminate delta T by simplifying. This is the relationship we come up. So we've derived equation 27.9 for lengths measured in directions parallel Lengths measured perpendicular are not contracted. So there is no length contraction perpendicular to the direction of motion. And the reason is that this reference frame is not moving with respect to the other. So you just don't see it. That's the long and the short of it.